Hey guys, Mrs. Horn here. Today we're talking about carbon and how we think carbon came to be, the shape of different carbon molecules, and examples of functional groups that have carbon in them. So let's get started. In the 1950s, Stanley Miller created a simulation, or he tried to mimic conditions that we think existed on early Earth. What he included in his setup was some water, which would have represented the primitive sea or the primordial sea. He had part of his setup to represent the atmosphere with methane and hydrogen and ammonia. And then part of his setup also included some lightning, which we do believe existed early Earth. Conditions were very abrasive and warm, and lots of storms and clouds and lightning very frequently, volcanic eruptions all the time. So the landscape of the Earth was very different from how it is today. But the question was, all things on life are made up of organic compounds, but we don't think those existed naturally. Not naturally, but we don't think those existed first. We think inorganic molecules were the first types of molecules that were on the planet. So Stanley Miller decided to create this experiment to figure out, well, how could you make an organic molecule from something that's inorganic? You have a spot here to draw the setup. I have put it on another page just so that you can see it a little bit bigger. I do need you to sketch something that looks similar to this. And I'm going to walk you through what each part means. If you need to pause it, go ahead and do that. This part of his experiment down here represented the sea, the primordial sea, and it looks like he's heating it up to have some of the liquid water evaporate and become water vapor. So this represents the sea. The part up here where it says water vapor, and even into this part of the container, that represents the atmosphere. So the atmosphere contains some of that water vapor, but it also contains hydrogen gas, methane, ammonia, and these are molecules that are coming from volcanic eruptions that were going on, so that's naturally part of the atmosphere. We also believe that there was a lot of harsh weather and a lot of lightning. So over here in this chamber, he was adding some sparks to represent the energy from lightning. After this chamber, he then cooled all of the materials that were in the atmosphere, and then we had some condensation. So this represents rain. So it's water, but also combined with any dissolved molecules that are in there. Now at the bottom of his setup, he had this little collecting flask, and in here he collected what looked like water. When he set it up, and you can't tell from here, it looked really cloudy. And he would test those samples every so often, and what we found is that there were actually organic molecules in there. So they were very early forms of organic molecules. So we're talking carbohydrates, proteins, and those organic molecules are present here, but were not found anywhere else on this setup. So by doing this experiment, Stanley Miller was able to conclude that, yes, in fact, organic molecules were made abiotically on an early Earth. Now let's continue to talk about carbon. Carbon makes up organic molecules, so that's why this whole section of notes is mostly about carbon. And when we mention those organic molecules that Stanley Miller was able to synthesize and find in that water, those molecules contained carbon. A hydrocarbon is a molecule that consists only of carbon and hydrocarbon. The name hydrocarbon makes sense. So it's made of carbon and hydrogen. And I have some examples of different ways that those can be organized. So you have 4 boxes there, and what I'd like in each box is a sketch of an example, and then I have little explanations next to them. So in the upper left hand box, I'm showing you a carbon skeleton that's just in a single line. So we've got our carbons kind of running right down the middle, nice strong skeleton, giving everything else structure around it. And the example that I have here is propane. This skeleton of carbons could be really long, it could be really short, but the idea is that they come in all different lengths. Over on the top right-hand corner, we have our molecule isobutane, and this is an example of how that skeleton can be branched. So here we have a carbon skeleton here, but then we have a carbon branching off of that main line of carbons. So skeletons can be branched, or they don't have to be. Now my bottom row here, bottom left-hand corner, I have a picture of the chemical structure of butene. And what you'll notice, hopefully you'll notice, is that this bond in here looks a little bit different. That's a double bond. So whereas everything else is a single bond, that is a double bonded, those are double bonded carbons in there. And then the fourth variety, I have cyclohexane here. The fourth variety of how you can arrange different carbon skeletons. This one is in the shape of a ring. And you'll notice that at the corner, I guess, of the ring, which a true ring doesn't have corners, but when we're talking carbon skeleton, they do. So at each corner of the ring, there is a carbon molecule. The next thing I want to talk about are functional groups. I've moved over to page 13. Functional group, it's a chemical group that affects the whole function of the molecule. So it's a part of a molecule that's kind of added on to an existing structure, and whatever that group is determines the whole function of the rest of the molecule. The first example that I have is a hydroxyl functional group. It's made up of only oxygen and hydrogen, so if I were to sketch it, that's exactly what it would look like. Here's a little bond, kind of waiting to bond with something else. My example is ethanol, and I've written the word ethanol, but I've also drawn out an example of what ethanol's structural formula would look like. And then one property of a hydroxyl group is that this is a polar molecule. On the rest of page 13, there are a bunch of other functional groups that I need you to, using the textbook, fill in the rest of this chart just as I've modeled it for you. On page 64 and 65 in the textbook, it's a 2-page chart with all of this information in it. So from that chart, you'll have to pull a sketch of each of these functional groups, an example, and then one property. It gives you a bunch of properties. I need you to read them and pick one to put in the chart. And this will take care of our information on carbon, and I hope this helps.